welcome students in the lecture series of some basic concepts of real analysis. In the last lecture, we will discuss monotone convergence theorem. For that, the statement for the monotone convergence theorem is a monotone sequence of real numbers is convergent if and only if it is bounded. Further, if the sequence is bounded increasing, then we have limit of xn is equals to supremum of xn. And if our sequence is bounded decreasing, then we have limit of yn is equals to infimum of yn. We also discussed about the first part, that is, if a sequence is convergent, then it must be bounded. Now, let us focus about the converse part. Conversely, let x is equals to xn be a bounded monotone sequence of real numbers. Then x is equals to xn is either increasing sequence or decreasing sequence. Consider two cases. Our first case is x is equals to xn is bounded increasing sequence, and the second case is x is equals to xn is bounded decreasing sequence. Now consider case 1. Since x is equals to xn is bounded sequence, then there exists a real number capital M greater than 0 such that the sequence mod xn is less than or equals to M for all natural number n. This implies that the sequence x is equals to xn has an upper bound in R, say M is an upper bound for the sequence modulus of xn. Now, recall the completeness property of real number. The completeness property of real number says that every non-empty set of real numbers that has an upper bound, it also has a supremum in R. Now, applying this completeness property, we can say that x star is supremum of the sequence xn for every n belongs to n. Say this is our equation number 1, as x star exists by the completeness property of R. Now, we will show that x star is equals to limit of xn. If epsilon greater than 0 is given, then we can say that x star minus epsilon is not an upper bound of the set supremum xn for all n belongs to natural number, because x star is the supremum. So, x star minus epsilon cannot be supremum for this set. Hence, there exists a member of the set, say xk, such that x star minus epsilon is less than xk. Say this is our equation number 2. As we know, x is equals to xn is an increasing sequence by our hypothesis. This implies that xk is less or equals to xn whenever n is greater than or equals to k. Say this is our equation number 3. Hence, from equation number 1, equation number 2 and equation number 3, we can conclude that x star minus epsilon is less than xk, and xk is less or equals to xn, and xn is less or equals to x star, and x star is less or equals to x star plus epsilon. Equation number 1 says that x star is equals to supremum. Equation number 2 says that x star minus epsilon is less than xk, and equation number says that xk is less or equals to xn, as this is our increasing sequence. So, we get our equation number 4. Equation number 4 again, x star minus epsilon is less than xk, and xk is less or equals to xn from equation number 2, and this term is less than x star from equation number 1, as x star is supremum of the sequence, and x star is less or equals to x star plus epsilon for every epsilon greater than 0 for all n greater than or equals to k. The equation number 4 can be written as modulus of xn minus x star is less than epsilon for all n greater than or equals to k. Hence, by the definition of convergence of sequence in real numbers, we conclude that the sequence x is equals to xn converges to x star. Now, consider the case 2. Case 2 is for bounded decreasing sequence. Let us say y is equals to yn is bounded decreasing sequence. Then we can say that x is equals to minus y, and minus y is nothing but minus of the sequence yn is bounded increasing sequence. From case 1, we can conclude that limit of x is equals to supremum of the sequence, and the sequence is defined as minus yn for all n belongs to natural number. Now, we get limit x is equals to minus of limit y. We have supremum of minus yn for all n belongs to natural numbers. This term is equals to minus infimum of yn for all n belongs to natural number. Therefore, we get limit of y, and the limit of y is equals to minus limit of x, and this term is equals to infimum of yn for all n belongs to natural number. The monotone convergence theorem establishes the existence of the limit of bounded monotone sequence. I repeat, the monotone convergence theorem establishes the existence of the limit of bounded monotone sequence. It also gives us a way of calculating the limit of the sequence provided we can evaluate the supremum and infimum respectively. Now, the geometrical interpretation of monotone convergence theorem. Geometrically, this means that if you graph a sequence that always moves in one direction, either up or down, and stays with a finite range, the graph will inevitably approaches a specific horizontal line, that is the limit. For example, the sequence x is equals to xn and xn is equals to 2 minus 4 upon n converges by the theorem as it is both bounded above and monotone, as we can easily check from the diagram. Now, our next topic is subsequences. For that, the definition is, let x is equals to xn be a sequence of real numbers, and consider the strictly increasing sequence of natural number defined as n1 is less than n2, n2 is less than n3, and up to so on. Then the sequence x dash is equals to xnk is called subsequence, and the sequence x dash is defined as xn1, xn2 up to so on. For example, x is equals to xn defined as 1, 1 by 2, 1 by 3 and so on. Then the selection of even index terms produces the subsequence, namely x dash is equals to xnk, and xnk is defined as 1 by 2, 1 by 4, 1 by 6 and so on. In this case, our n1 is 2, n2 is 4, n3 is 6 and so on. Our first result for the subsequence is, if a sequence x is equals to xn of real numbers converges to a real number x, then any subsequence x dash is equals to xnk of x also converges to that real number. Let us start with the proof. A sequence x is equals to xn in real numbers r is said to converge to a real number x if for every epsilon greater than 0 there exists a natural number k depending upon epsilon such that we have modulus of xn minus x is less than epsilon for all n greater than or equals to that natural number. Say this is our equation number 1. We need to show that the subsequence x is equals to xnk of x is also converges to this real number, say x. Since by the definition of subsequence we have a strictly increasing sequence of natural number, that is n1 is strictly less than n2 and n2 is strictly less than n3 and up to so on. So, by the principle of mathematical induction, we can easily say that NR is greater than or equals to R. Say this is equation number 2. Hence, if R is greater than the natural number k, which is depending upon epsilon, then from equation number 2 and equation number 3, we can easily check NR is greater than or equals to R and R is greater than or equals to k depending upon epsilon. Recall the equation number 2 and equation number 3. Equation number 2 says that NR is greater than or equals to R and equation 3 says that R is greater than or equals to K depending upon epsilon. If we club these two equations, we get this result, that is NR is greater than or equals to R and R is greater than or equals to K and K is depending upon epsilon, such that modulus of x and k minus x is less than epsilon. Again, by the definition of convergence of sequences in real numbers, we can conclude that the subsequence x dash is equals to x and k of the sequence x also converges to x. Our next result is, let x is equals to xn be a sequence of real numbers, then the following statements are equivalent. Our first statement is the sequence x is equals to xn does not converge to x belongs to R. Our second statement is there exists an epsilon naught greater than 0 such that for any epsilon there exists a natural number n k such that we have modulus of x and k minus x is greater than or equals to epsilon naught for all n k greater than or equals to k. I repeat the second statement, there exists epsilon naught greater than 0 such that there exists a natural number n k, we have modulus of x and k minus x is greater than or equals to epsilon naught for all n k greater than or equals to k, where k is also a natural number. Our third statement is there exists an epsilon naught greater than 0 and a subsequence x dash is equals to x and k of x such that we have modulus of x and k minus x is greater than or equals to epsilon naught for all n belongs to natural number. So, we need to show that these three statements are equivalent. So, we prove by A implies B, B implies C and C implies A. So, let us start with the proof. First, we will show that statement 1 implies statement 2. Our statement 1 is the sequence x is equals to xn does not converge to x, where x belongs to R. So, using this, the sequence x is equals to xn does not converge to x, where x belongs to R, then for some epsilon naught greater than 0, it is impossible to find a natural number k such that for all n greater than or equals to k, the term xn satisfies modulus of xn minus x is less than epsilon naught. So, we cannot find that natural number as the sequence x is equals to xn does not converge to x. That is, for each x belongs to n, it is not true that for all n greater than or equals to k, the inequality hold, that is modulus of xn minus x is less than epsilon naught. In other words, we can say that for each k belongs to natural number, there must exist some another natural number n k which is greater than or equals to k such that we have modulus of x and k minus x is greater than or equals to epsilon naught. This is our statement number 2. Secondly, we will show that the statement B implies statement C. Now, recall the statement B. Statement B is, let there exist an epsilon naught greater than 0 such that for any k belongs to n, there must exist some natural number n k we have modulus of x n k minus x is greater than or equals to epsilon naught for all n k greater than or equals to k, and we need to prove that there exists epsilon naught for the subsequence of x such that this inequality holds, that is modulus of x n k minus x is greater than or equals to epsilon naught for all n belongs to natural number. Let us start with the proof. Let n1 belongs to the natural number such that n1 is greater than or equals to 1 and modulus of xn1 minus x is greater than or equals to epsilon naught by the given hypothesis as there exists nk belongs to natural number. In similar way, for n2 there exists such that n2 is greater than or equals to 2 and modulus of xn2 minus x is greater than or equals to epsilon naught. Further, let n3 belongs to the natural number such that n3 is greater than n2, which is greater than or equals to 2, and we have modulus of xnk minus x is greater than or equals to epsilon naught. Now, continuing in this way, we obtained a subsequence x dash is equals to xnk of x such that modulus of xnk minus x is greater than or equals to epsilon naught for all n belongs to natural number. We can see that this is our desired result. Now, we will prove that our statement number C implies statement number A. Our statement C says that there exists epsilon naught greater than 0 and a subsequence x dash is equals to xnk of the sequence x such that we have modulus of xnk minus x is greater than or equals to epsilon naught for all n belongs to natural number. We need to prove that the sequence xn does not converge to x. If x is equals to xn, let us suppose if x is equals to xn converges to x, then the subsequence x dash is equals to xnk of the sequence x would also converge to x. But this is impossible since none of the terms x dash is equals to xnk belongs to the epsilon naught neighborhood of x. Hence, we can say that the subsequence x dash is equals to xnk does not converge to x. That implies the sequence x is equals to xn does not converge to x. Now, our next topic is divergence criteria. Divergence criteria says that if a sequence x is equals to xn of real numbers has either of the following property, then x is equals to xn is divergent. First property is x is equals to xn has two convergent subsequences, say x dash is equals to xnk and x double dash is equals to xnr, whose limits are not equal. And the second property is if x is equals to xn is an unbounded sequence. In either case, we can say that our sequence is divergent. I again repeat the statement of divergence criteria. Sequence x is equals to xn is divergent if it satisfies either of the following conditions. First condition is x is equals to xn has two convergent subsequences whose limits are not equal, and the second property is x is equals to xn is an unbounded sequence. For example, the sequence x is equals to minus 1 to the power n for all n belongs to natural number is divergent, as if we expand this sequence we get minus 1 comma 1 again minus 1 comma 1 and so on. Then we have two subsequences, say x dash is equals to minus 1 comma minus 1 comma minus 1 up to so on, and x double dash is equals to 1 comma 1 comma 1 and so on. As we can say that both are the constant sequence and constant sequences are converges to itself. So, we can say that x dash converges to -1 and x double dash converges to 1. The subsequence x dash of x converges to -1 and the subsequence x double dash of x converges to 1. Therefore, we conclude from the divergence criteria that the sequence x is equals to -1 to the power n is divergent. Our another example is x is equals to 1 comma 1 by 2 comma 3 comma 1 by 4 comma 5 comma 1 by 6 and so on is divergent. Now, consider the given sequence. Given sequence x is equals to xn is xn is equals to n if n is odd and xn is 1 by n if n is even. It can be easily seen that the sequence x is equals to xn is not bounded, as we can see that for the odd positions the sequence is xn is equals to n for all n belongs to natural number. So, we can say that the sequence x is equals to xn is not bounded or unbounded. Hence, again by the divergence criteria we can say that the sequence is divergent. Now, the Cauchy's criteria. Let us start with the definition of a Cauchy sequence. A sequence x is equals to xn of real numbers is said to be a Cauchy sequence if for every epsilon greater than 0 there exists a natural number h depending upon that epsilon such that for all natural numbers n and m greater than or equals to h depending upon epsilon such that the terms xn and xm must satisfies the following inequality, that is modulus of xn minus xm is less than epsilon. I repeat the definition of Cauchy sequence. A sequence x is equals to xn of real numbers is said to be a Cauchy sequence if for every epsilon greater than 0 there exists a natural number h depending upon that epsilon such that for all natural numbers n and m greater than or equals to h depending upon epsilon such that the terms xn and xm satisfies modulus of xn minus xm is less than epsilon. Geometrical interpretation of Cauchy sequence. Geometrically, it means that the term of the sequence get progressively closer to each other, clustering around a specific region on the number line, even if that region's exact location is not yet known, as we can easily check from the diagram. Our first result for the Cauchy sequence is x is equals to xn is convergent sequence of real numbers. Then x is equals to xn is a Cauchy sequence, or in other terms we can say that every convergent sequence is a Cauchy sequence. Let us start with the proof. If limit of x is equals to limit of xn is equals to x, then by the definition of convergence of sequences in real numbers, we can say that for every epsilon greater than 0, there exists a natural number k depending upon epsilon. In this case, we choose our epsilon is epsilon upon 2 because we have two terms xn and xm. So, there exists a natural number k depending upon epsilon upon 2 such that for all n greater than or equals to k depending upon epsilon upon 2, the term must satisfies mod of xn minus x which is less than epsilon upon 2. Thus, if h is equals to k and h is depending upon epsilon and k is depending upon epsilon upon 2, and for natural numbers n and m greater than that natural number h which is depending upon epsilon, we have modulus of xn minus xm is equals to modulus of xn minus xm plus x minus x. This is nothing but modulus of xn minus x plus x minus xm. If we apply triangular inequality in this equation, we get modulus of xn minus xm is less or equals to modulus of xn minus x plus modulus of xm minus x, as we can say that by the definition of Cauchy sequence, mod of xn minus x is less than epsilon by 2. Substitute this value here, we get this term is less than epsilon by 2 plus epsilon by 2. Hence, we get modulus of xn minus xm is less than epsilon for all natural number h depending upon epsilon. We conclude that the sequence x is equals to xn is a Cauchy sequence. Now, again recall the definition of a Cauchy sequence. Our Cauchy sequence is the sequence x is equals to xn of real numbers is said to be Cauchy if for every epsilon greater than 0 there exists a natural number h which is depending upon epsilon such that for all natural numbers n and m greater than or equals to h and h is depending upon epsilon, the terms xn and xm must satisfies the inequality modulus of xn minus xm is less than epsilon. As we already know the geometrical interpretation, we can easily check the figure. The geometrical interpretation is, it means that the term of the sequence get progressively closer to each other, as we can see in the diagram, clustering around a specific region on the number line, even if that region's exact location is not yet known. Thank you. We will discuss in the next lecture.